Hello, everyone. This is the Space Cafe podcast, and I'm Marcus. We have been actively searching for ET for more than 60 years now, with all the fancy tech we've been developing ever since. So the question that seems obvious is, have we come any closer? Is there anything that we know today that was not known then? And the surprising answer is yes. There's a lot we know today that we did not know then. My guest today is no other than Dr. Pascal Lee, prominent planetary scientist at the SETI Institute, NASA Ames Research Center, and the director of the NASA Haughton-Mars project. And we left literally no stone unturned. We looked everywhere, even the underground caves of Mars and the icy moons of Saturn, in our quest for extraterrestrial life. I've been profoundly and really looking forward to releasing this gem to you guys. Please enjoy wherever you are in this galaxy. Have we made any progress so far? Are things any different when it comes to our knowledge of extraterrestrial life as opposed to 61?
Yeah, so, the SETI effort, SETI, the search for extraterrestrial intelligence, started in the early 60s, really, by Frank Drake, with Frank Drake. Frank Drake is considered to be the father of SETI. He was an American astronomer. And Frank Drake convened an interesting workshop at the time to bring the astronomy community together and explore the question of our chances of finding an intelligent civilization out there. So he was a radio astronomer. And so the assumption there was that we were trying to get a sense of our chances of detecting a civilization that would be using radio waves to communicate. And so he convened this workshop, and he divided the workshop into different sessions where one group would focus on the number of stars and the rate of star formation in our galaxy. And then a second group in a different session focused on the question of, what are the chances of stars having planets? And then another session was dedicated to, once you have a planet, what are the chances, how many planets in a planetary system should be expected to have an environment that's suitable for life? And then another session, once you have conditions that are suitable for life, and presumption there was you have water, liquid water, on, substantial amounts of time, what fraction of these planets would evolve life? And so then another session was dedicated to the question of, once you have a planetary system, how many of these planets within a planetary system would be suitable for life? And by that, we understood that it would be an environment in which liquid water would be present stably for long periods of time. And then once you have a planet that is suitable for life, what is the fraction of these on which life would actually emerge? So that was another session. And then another session discussed the notion that once you have life that has emerged, what fraction of these would see intelligence emerge? And of course, you have to define intelligence. And then once an intelligent form of life has emerged, what fraction of these planets with an intelligent life form becomes an advanced civilization? And by that, the definition, it was a civilization that is capable of radio communications. So even on Earth, we are an advanced civilization only 4th century or so. Before that, we were not capable of radio communications. And so So we were intelligent, but we were not an advanced civilization. And then finally, what is the average longevity of a civilization? And so historians were brought in as well. And the workshop was organized in such a way that Frank Drake realized that you could, with these different sessions, essentially organize them in an equation. And that became known as the Drake equation. It's arguably one of the most famous equations after, F equal ma by Newton and E equals mc squared by Einstein. It became the Drake equation. The Drake equation, it gives you the number of advanced civilizations in our galaxy right now as the multiplication of 7 terms. So mathematically, it's very simple. You just multiply 7 terms. And these 7 terms are the rate of star formation in our galaxy times the fraction of stars with planets times the number of planets within a planetary system that have conditions suitable for life, meaning liquid water, times the fraction of those on which life actually emerges, times the fraction of those on which life actually becomes intelligent, times the fraction of those where intelligent life becomes an advanced civilization capable of radio communications. And by the way, doesn't necessarily engage in it, but is capable of it. Finally, times the average longevity of a civilization. If you knew the value of each one of these 7 terms, you would get the number N of advanced civilizations in our galaxy. So it's a very powerful equation. And when I got hired at the SETI Institute, Frank Drake was in the boardroom. I gave a talk. And at the end of my talk, he leaned over to his assistant and said, okay, we're going to hire him under N sub E, which is the number of planets that have habitable conditions, meaning liquid water, within the planetary system. And that's because I was interested in the Earth, Mars, the history of water on planets, and of course, the possibility of life. But interestingly, the SETI Institute hires scientists who address one or more terms of the Drake equation. And so we have sociologists and historians who study the longevity of civilizations. We have people who are doing deep space astronomy, who study the rate at which stars form in our galaxy. And of course, we have planetary scientists who study planets and exoplanets around other stars. So where does SETI stand today? Well, the search is going on. We are still focusing on mostly nearby stars within our own galaxy, but the SETI Institute now has the Allen Telescope Array, the ATA, donated largely by Paul Allen, which is why it has that name. And
Microsoft, Paul Allen.
That's right, co-founder.
Yeah.
And the Allen Telescope Array is conducting a survey of nearby stars, but through many channels, frequency channels, in hopes of detecting some anomalous broadcast. And I think it's an effort that's definitely worth doing. There have been no findings yet, but the search is on. I personally have a bit of a unusual perspective, I think, on this, which is that I don't think our chances of finding an advanced civilization in our own galaxy to be very high. I've argued that while all the terms of the Drake equation might actually make you quite optimistic, there's one term based on the one data point that we have here on Earth. So it's a very limited body of experience, but nevertheless, it's a data point, and therefore not a speculation. The data point is that intelligent life on a planet is likely very hard to occur. And so I argue that in large part because life appeared very early on Earth, life itself in microscopic form and primitive and relatively simple form appeared very early in our planet's history, almost immediately as soon as liquid water was stable at the surface of the Earth. We have in the oldest rocks of Earth that were laid down originally in a water environment, they have biochemical signatures of life in them. And so life itself is probably relatively easy to see occur once liquid water conditions are right. However, it took a long, long time for life on Earth to yield something like the human being. And you can define intelligent life by defining it as, the emergence of a life form that is capable of using technology to really alter its environment. We're not talking about the beaver who conducts a dam or a bird that builds a nest. We're talking about something that can, create a tool and all of a sudden expand its hunting realm, or create or master fire. So that took a long, long time for it to emerge on Earth, and it was not at all an automatic path. It was very circumstantial. There was no particular imperative. Life did just fine without any creature knowing how to master fire for, billions of years, literally, on our planet. But
in fact, it's like 99% of the entire lifespan of life on Earth is, in fact, the no fire, the no intelligence, the no technology. Yeah,
and life was just fine. You could argue that
exactly.
if it was an imperative of life, it would have appeared a lot more commonly and faster, but it did not. And the way it appeared actually seems to have been tied to a number of circumstances, in particular, a very late giant impact on Earth. Dinosaurs had ruled the planet for hundreds of millions of years. No fire-making creature ever emerged. No weapon-developing creature. And then, next thing you know, the dinosaurs get wiped out by this giant impact. And it opened the way for small mammals to evolve. Mammals had been very bottom of the totem pole of the food chain. And all of a sudden, one glorious day, the dinosaurs were gone. And so they evolved. And of course, at some point, it became an advantage for one of the mammals to stand upright, run.
And fill that niche.
It unleashed exactly the, Homo erectus appeared. So that was about 1 million to 2 million years ago. Homo erectus, so could make tools, could make fire, and started migrating. And so that is what makes me, if you look at how long we've had intelligent life on Earth, the 1 or 2 million years of Homo erectus compared to the age of the Earth, as you pointed out, it's a minute fraction. And that is what makes me think that if you do the numbers in the Drake equation, the fraction of planets, even if they have life on them, where life actually becomes intelligent, is probably very small. And in spite of how many planets we're finding now around nearby stars, people sometimes say, well, we have so many exoplanets now, we must have intelligent life out there. This was the assumption all along, that planets were common. However, I think this analysis of the fact that intelligent life, at least on Earth, took so long to show up, and I think that's something that is probably universal when it comes to life, means that if you do the math, n equals 1 in our galaxy. N equals about 1. So I find that an astounding number, because we are it, possibly. Or even if I was off by a factor of 10, I mean, we'd be, for all intents and purposes, very isolated. If there's only 10 advanced civilizations in our galaxy, like ourselves, or more advanced, the average distance between them would be about 30 to 40,000 light years. I mean, you send a signal, it's going to take 40,000 years to get to that planet. If they respond, it'll take another
40,000 years.
Okay, so if they care, so
yeah,
my point is we're not at all living in a Star Warsian or Star Trekian
Yeah. Yeah.
And
Populated universe.
that's right. It's a cultural shift because, we always think, well, we should be really open to the possibility of intelligent life out there. But and culturally we want to grow a global melting pot here on Earth, which is good. And we think we sort of project ourselves into the galaxy by thinking that there are bars where different civilizations hang out and come play music. But it's not like that.
Yeah.
It's actually not like that.
Yeah.
We are profoundly alone.
Yeah.
And in our own galaxy, there's probably lots of planets with life, but mostly primitive life. Lots of planets with moss, innumerable planets with oceans, with bacteria in them, cyanobacteria in particular that might be photosynthesizing. There must be many planets with amazing beasts and jungles or deserts and ice fields with.
Why do you think there must be?
Well, because
why is that?
This sort of a statistical argument, but you're right, we don't know. But the thing about, because life appeared so early in Earth's history, the suspicion is that it's a relatively easy process that leads to life. And so life itself is unlikely to be uncommon. I wouldn't be surprised if we found life within our own solar system that is independent of Earth life. I wouldn't be surprised if we found microbes in the deep underground of Mars or in the oceans of Europa and, Enceladus. So, there's plenty of life for us to explore out there. But running into something that is intelligent, Homo erectus, in terms of ability or more, is going to be very rare. And let alone becoming an advanced civilization. Now, once you have reached the Homo erectus stage, becoming an advanced civilization took almost no time. I mean, 1 million years is nothing. And we became, I think, an advanced civilization with the Scottish physicist James Clerk Maxwell.
Yeah,
I mean, it's a bit silly to point it out the single person, but he came up with the Maxwell's equations, which describe for the first time properly the way electromagnetic waves propagate. So not just light, but also radio signals. And so James Clerk Maxwell established his equations in 1864. So you can argue that since then, we understand what radio waves are, we can generate them, and we can begin to be heard by other civilizations.
Some argue that any technological civilization is bound to come to an end because they won't make it to that filter of technology, because any technological civilization will ultimately destroy itself.
So
as we are,
you bring up a good point.
As we are currently trying. Yeah.
You bring up a very good point. When I come up with n equals 1, the assumption for the average length of a civilization is 10,000 years. Now, why 10,000? Well, first of all, no single civilization on Earth has lasted really more than anywhere from a few hundred to a couple of thousand years as a single sort of cultural civilization. Now, humanity, in a sort of a broader sense, if we consider ourselves to be the same civilizations as, the early Egyptians, we've been around then for about 5,000 years. So, you can claim, and that's what some people do, that in the Drake equation, the average longevity of a civilization is 1 million years. But you have no basis for claiming that. It's completely speculative. I mean, why not 10 million? Why not 100 million years? We don't know. But we do know that civilizations tend to destroy themselves and sort of press a restart button every few hundred to few thousand years here on Earth. So I'm thinking that by putting in 10,000, I'm definitely biased, of course, towards Earth civilization. But at the same time, it's the only data point we have, really. Now, if you increase that number, if you instead of saying 10,000 years, you think on average civilizations live 100,000. Well, then instead of one civilization in our galaxy, there would be 10. If you want the longevity to be 100,000 years per civilization, then we have 100 civilizations in our galaxy. But even at 100 civilizations in our galaxy, the average distance between two civilizations would be about 2,000 light years. So that's considerable in terms of distance to travel or even communicate. And then, of course, some people think that we can live, 100 million years as a civilization. So that, of course, will come with very different technological leaps, presumably. At that point, a single civilization might actually conquer the rest of its galaxy on those time scales. And now, even though you might have had only one civilization at first, now you have essentially several across the galaxy because of that migration. So those are complexities that, of course, have to be taken or have to be considered. But at this stage, we are approximately halfway through the life of our star and approximately 1/4 of the way through the life of our galaxy. In fact, we're actually about halfway through the life of our galaxy too, because our star is a second generation star. But even with one civilization per galaxy, there are out there at least 100 billion galaxies. So in the broader universe, we're not
our galaxy.
I'm pretty sure about that. Okay. But
statistically.
That's right, statistically. Yeah. But we're just much rarer than we think. And, we should adjust our science fiction fantasies and lores to sort of reflect that. Now, this is why I think that SETI, this business of listening to intelligent civilizations out there, should really focus on other galaxies. Because, if you look at the Andromeda galaxy, for example, which is the closest large galaxy next to our own galaxy. Andromeda galaxy is a swarm of about 300 to 400 billion stars. The Andromeda galaxy, if you could see it with the naked eye more brightly, would be about 6 times wider across the sky than our moon. It's really a gigantic wheel of stars right there in our sky. We don't see it because it's about 2 million times dimmer than the moon. Okay, so we only see a fuzzy little blob. But if you could see the full brightness of the Andromeda galaxy with all its stars, it would be a huge object in our sky. And my point about this is that if you point a radio telescope at something like that, you are listening, you're scanning basically the signals of hundreds of millions of stars at a time, depending on where you point. And that actually could really speed up the search for something. But of course, the signals be much weaker than within our own galaxy, much weaker.
But Pascal, let me ask you this. Considering those distances and considering our feeble minds as still very young species, on this planet, the question is, even if we found an interesting signal in the Andromeda galaxy, what would we do with it? I mean, it can only lead into massive frustration because it takes, what's the distance? So what would be the closest distance to the Andromeda galaxy?
The Andromeda galaxy is about 2 million light years away.
Exactly. So 2 million years. I mean, this is the inception of Homo erectus, what are we talking about here? I think this is one of the key problems, and maybe the hybris of humans, that we think we can understand anything and science will find an answer and a solution. But this, I think, is a profound limit where we have a profound problem to get over. Because I mean, like 2 million years, speed of light. If we do not find a solution how to go faster than the speed of light, which maybe not out there, whoever, I don't know.
So
I
I agree with
no,
you
go ahead.
that there's this proportion sometimes between these scientific questions and the reality of our lives and our lifespans on Earth. But there's a big difference in science between awareness and understanding. If we actually detected a signal from Andromeda that we could say is definitely artificial, that we could, make sure that it's not some military satellite that we're mishearing, but we actually could repeatedly detect a signal coming from the Andromeda galaxy. Well, first of all, that would establish the fact that we are not the only advanced civilization in the universe. I mean, that is a big, even if we don't understand what they're saying, you can tell if the signal is if it's modulated, there are many complexities to an artificial radio signal. So
it would change our
exactly.
self-understanding.
So just being aware, as opposed to speculating that we are alone or not alone, just being aware that there's actually something out there, even if that signal left that galaxy 2 million years ago, and those people might not even be there anymore, or they might still be there, and in fact, they might be on their way. All of this,
exactly, because we've been waving.
All of this is very exciting, and they would not be aware of us because, unless they could travel, and could come visit us, they would not be aware of us because we haven't ourselves been radio loud and revealing our presence with radio waves, which is really one of the few ways you can actually make yourself known. I mean, other than from far away, you can see that the Earth has an oxygen-rich atmosphere. So we know that it's a planet that has life if you're looking at the Earth from far away, like, from other stars. But you can't necessarily tell that, although in a couple last centuries, you can now tell that there's probably pollution in the atmosphere that's a bit weird. But you basically can tell that it's a planet with life, but you can't necessarily tell that it has intelligent life on it. So they would not necessarily know about us. In fact, nobody beyond about 100 light years would have received radio signals from the Earth yet. If we detected something coming from Andromeda, that I think even if we don't understand what they're saying, even if we don't comprehend the monumental distances and the possibilities of where they might be now, it's still a very important step in science and in understanding our place in the universe. So, and meanwhile, it doesn't take a lot of effort. I mean, you just have to do the listening. And I think it's very exciting. And of course, we do this for ourselves more than really to communicate with them. We don't even know if it's wise to communicate with them or even try. But we do this for ourselves so that we understand better who we are, how unique we are, how special, to me, one of the most profound implications of us being probably alone in our galaxy as an advanced civilization is that it should give us a really profound sense of responsibility. Nobody's going to come rescue us. We're not going to be invited to join a galactic, federation anytime soon. Starship Enterprise is not going to show up, uncloak, and somehow give us, the warp drive. We have to be responsible for our own planet. We have to explore responsibly, and we have to explore. That's the thing. We have to go beyond our own planet and see what's out there. I wish I was born, a few thousand years from now, and could go on some more of these journeys where we're exploring other worlds around other stars.
You think that we will ever, from a technological perspective, get to travel to different galaxies? I mean, like, still, it's the constraint is a technological constraint. The constraint is still Einstein. Do you think we can go beyond that at some point?
The laws of physics, as we know them and understand them for now, are very limiting in that regard. But until the next breakthrough. But we don't know if it will ever happen. We could be basically against the wall here. Just to give everybody a sense of how far stars are, if and sorry for taking an American-centric example, but if the sun was the size of a grapefruit, the sun was the size of a grapefruit, and you put it at the edge, at the beginning of the Golden Gate Bridge in San Francisco, California. Okay, Pluto, one of the most distant planets from the sun, is going to be at the distance. It's a tiny little pinhead at the distance of the first pillar of the bridge. Okay, so about 300 meters away. Okay, the next star is not even a grapefruit. It's smaller than that. It's more the size of a little apricot. The next star is Proxima Centauri. It's a red dwarf. It's located 4.26 light years away. And at that scale, that next star is located in Chicago. Oh, I wish I had a European example of where Chicago is in relation to San Francisco, but it's several thousand kilometers away. Okay. It is mind blowing.
This is mind blowing.
So right this minute, if you were to ask me, what does the future of interstellar travel look like? I would say that the only way it seems really possible in the future is if we send humans who are no longer biologically like us, but who are intelligently like us. We live in, it sounds a little cliche, but we live in an age where we still make a distinction between humans and robots, intelligence and artificial intelligence. But it's all going to blur. It's all going to blur. We're going to start seeing androids and humanoids.
It's blurring as we speak,
As we speak. We live in this incredible age where it's happening right now. We're going to see very soon the creation of physical artificial humans who look just like us, who react like us, who might even be molded after people we know or our family members maybe, or some famous, scientist, whatever. I think that we're going to get to the point where the line between humans and artificial humans is going to really get blurred, because we are going to be able very soon to create avatars of ourselves and creatures that are essentially not biological humans, but entities that we can relate to as if they were humans. So that we can even create them in the image of people we loved, who might be gone, or in the image of, famous people of the past. The point here is that we're on the verge of being able to create artificially humans who would react just like another human being would. I mean, you're talking about just, artificial intelligence, and who might actually provide the emotional relationships that, some of us seek, who for all intents and purposes would be humans. In fact, the best example of that is the character Data, I think, in Star Trek, The Next Generation. I don't know if you are familiar with that. So, I think we're on the verge of seeing a broader definition of a human being, where we are going to accept in our society artificial humans as being human beings. They will be people that we could live with. We can communicate with them. We can share emotions. To me, one of the earliest incarnation in pop culture of something like that is the character Data in Star Trek: The Next Generation, because we all understand he's a robot, but we treat him like a human. He seems to have emotions. We can completely relate to him. We feel sad when he is sick or broken. We feel happy when he is fixed. And at some point, you realize that a creature like that is your offspring. I mean, we adopt children, we adopt dogs, we accept in our lives things that are not biologically related to us directly. And I think we will be able very soon as a society to adopt in our lives beings that are essentially artificial, but whom we might treat as our offspring. And so I think the time for interstellar travel will come when we have humans that we could send as our ambassadors. They will be created in the image of humans on these journeys.
Or maybe we're not talking about humans. We're talking about a new iteration of humans.
Yes.
Because it's a new level then. So it's not that humans are traveling to that different star system or to that different galaxy. It's in fact that intelligence is traveling, and the substrate, so to say, is a different one.
Yeah. Well, although you could argue that it is us, because I see your point. It's technically not us, not our biological cells, but our technological replicas. But because they're going to be so tied and connected to us, we will see them as our representatives. We will accept them as our representatives. In fact, some people are not very excited about robotic exploration of space. They want to see humans go. But once you have humans once you have human boots on the ground, once you have humans like that, it becomes humanity going. And again, it's I think we all understand that biological evolution might be coming to an end for humans, in the sense that the normal pressures of evolution are no longer really driving biology. I mean, we survive illnesses. We have all kinds of technology that allows us to overcome what biological evolution would normally limit us to. It still remains possible that biology could make us age a lot slower and have much longer lives and not become eternal or immortal, but that's still a possibility, of course. But otherwise, having humans that are essentially artificial, that have no expiration date, who are repairable indefinitely, that's a good characteristic for interstellar travel. And then where you can be turned off, for the long, boring. You don't consume as much
for the long haul.
For the long haul, yeah, exactly. And so maybe this is it. This is the next step of biological evolution, which is technological evolution of biology.
But still, those guys would still need to travel for 2 million years. Not defrozen.
They might be actually able to travel quite a bit faster, undergo accelerations that we would normally not survive ourselves. They might also be, you could possibly send just one or two, but then a whole bunch of chips to populate a much larger group. And then once they get to the other end, they assemble the others. So you could imagine all kinds of ways that could make their traveling a lot faster and compact. Also, by then, hopefully some progress will be made with propulsion. We just understand that even with progress in propulsion, at this point, if we look at humans traveling to other stars biologically, we have to be looking at multi-generational starships, where the people who leave are going to die, and eventually people who get there might not even be born yet. Uh, but with artificial humans, that opens the door to all kinds of to faster travel, more compact packaging of humans, no consumables along the way, just turn things off, and you could accelerate something like this electromagnetically, and launch it into deep space much faster. So I still think that we're looking at very long travel, but it could actually be quite manageable for what we're sending off. And then imagine we send this off in different directions to different promising exoplanets. Once they get there, these artificial humans could start creating biological humans. Just because we would have traveled with them genetically, they can. It's all science fiction-y, but we're also looking at sort of a more distant future. And I think if you can imagine it, you can probably create it.
Create it. Would it be possible to go like fiber optic type of information transfer? So, for example, you use lasers to assemble matter into a form of your liking in situ. So, for example, you use a laser to race across the universe at the speed of light, and on your target or at your target, you use that laser to assemble the dust into a robot or a human-like.
Yeah, it's interesting you say that. It's sort of it's 3D teleprinting.
Yeah, exactly.
Teleprinting, right? So you remotely print something in 3D, and that's actually a potential option. I mean, there are issues with power loss of lasers over long distances. You'd have to have a lot of power at the start to have something that's still potent at the end and still really focused. But that's an intriguing possibility. I mean, I could see us doing this on the moon, for example, on our moon. Teleprinting something from Earth on our moon. But that's a much shorter distance where lasers will not dampen too much. Anyway, hey, who knows? I don't claim to have any any answers at all.
It's fantastic. But Pascal is fantastic. I love nerding out about those topics. Still, let me get back to the beginning of our conversation when I asked you, is there anything different today as opposed to the 60s when the SETI program started? Is there anything we know today that was not known back in the day related to extraterrestrial life or the potential for extraterrestrial life?
Yes. It comes down to the Drake equation. We know a lot better now how many stars have formed in the history of our galaxy. And that was an important number to nail. We now know that life appeared. Well, we now know that planet formation is a very common process. We suspected it all along, but now we see exoplanets pretty much around every star. Not quite. Some stars are not, conducive to having planets around them, but pretty much the planet phenomenon is a very common thing. We also realize now that 10 planets is not even covering it. Our own solar system, we depending on how you define planet, we have, tens of planetary bodies, things that are over 1,000 kilometers in diameter, for example, which are places where liquid water can be stable for a long time, if you're over 1,000 kilometers in size. We now have a better handle on how early life appeared on Earth. I mean, in the 60s, we knew about ancient rocks, of course, but now we have dating techniques. We understand that life appeared within the first few 100 million years of the Earth itself being formed, after the formation of the moon. We now also have a better handle on when intelligent life appeared on Earth. When did humans actually start mastering fire? We now know it's about 1 million years ago in East Africa, et cetera, et cetera. So, what we haven't learned a lot about is really the longevity of a civilization. I mean, that's still very speculative. And then any number is arguably good. But we do realize, I think, that some scenarios of our mortality are actually quite possible. For example, nuclear war was often what was being feared the most in the 60s as sort of why civilizations might not last for very long. But we now realize that pandemics are still something that we are vulnerable to. I mean, of course, in the Middle Ages, you had the plague and all this, but look at COVID. COVID could have been much worse. COVID could have been much more lethal.
I mean, think like Spanish flu 100 years ago.
Exactly. So, and these things have a way of showing up. So that actually.
Then we also got population decline. Some argue that we're increasingly facing a problem of global population decline, which also means a civilization coming to an end, maybe restarting, rekindling something new. But this is also an existential risk, I think.
Yes. And then, we now have a good handle on whether or not we could be wiped out by an asteroid or not.
Yeah.
We think we know of all the asteroids in our solar system and comets that are anywhere near capable of wiping us out in sort of a global way, and there are essentially none for now. But we are vulnerable
until another Oumuamua comes around out of nowhere.
However, exactly, we have now these interstellar things that are very unpredictable, and of course, you'd have to be very unlucky. But hey. Why did the dinosaurs die? It's because they did not have a space program.
Yes.
So thankfully we have a space program. Hopefully we won't be as unlucky. But
we got the fascinating Hera, the planetary defense mission going on between the DART mission and the Hera mission. So I think we're pretty much gearing up our game to be able to defend ourselves.
I agree.
Yeah.
So these are all developments which allow you to sort of have a better understanding of our universe, of our chances of finding ourselves. I mean, we could still be living in a galaxy where somehow there would be a lot of civilizations, but I would be really surprised. And it would mean that the Earth's path and evolution of life on Earth and intelligence on Earth was unusually slow and,
But Pascal, I to be super honest, I don't need so much to be happy, because I wouldn't expect I wouldn't even search for any intelligent life out there. I would just search for a single cell. I'd be already very happy about finding a single cell.
Well, tell me about it, which is why Mars is so interesting. And which is why I spent most of my life studying Mars. Yes, because you're right. So that alone would be a very important discovery.
So are we looking in the right places on Mars? Do we need to dig deeper?
So we are not looking in the right places on Mars, and it's even worse than that. I personally think that we're not looking for the right thing. Let me explain. In the early 70s, the U.S. space program sent the first 2 landers on Mars, Viking 1 and Viking 2.
Yeah.
They had a very clear goal to look for life that was still alive on Mars. Now, of course, we don't know if there's life that's alive on Mars, but that was the mission. It was a biological mission. They went there to look for signs of life that was alive. And they scooped up soil. They gave it nutrients. They did that again after baking the soil to make sure anything that would have lived in it was dead, and see if it would take in the nutrients.
So they literally watered the soil and tried to find out if something grew out of it?
They gave it some moisture, yes. Yeah, yes. But ultimately, one experiment concluded that it might have detected life, and the other 2 or 3 experiments concluded that it was more likely to be some unusual form of chemistry and not life. The consensus now is that it's probably some complex chemistry that has to do with superoxide, which is why the Martian surface is so red and rusted. So it's replete with oxides. So oxides have a way of, behaving like there's something alive, but it isn't. It's just very reactive chemically. But that was it. And the Vikings concluded that Mars had no life, which I think is not entirely established. At least it was at even as far as the surface is concerned. But that's what they concluded. And the rest of the missions have been looking now for past signs of life, ancient habitable environments. And the thing that I keep saying in meetings with my colleagues is that even if we found life on Mars today in the form of a fossil, let's say, Perseverance is driving, through a road cut and giant bones were sticking out of the rock face, you could not conclude that that is alien life. In other words, that it's life that's independent of life on Earth.
How so?
If you saw giant bones sticking out, you'd still write a paper to Nature or Science, okay? But you could not establish that it's for sure alien life, and that's because Earth and Mars are not isolated. We have on Earth over 300 meteorites that have come from Mars on their own. I mean, they got ejected from Mars by Mars getting hit by asteroids or comets. These things take anywhere from a few months to 10 million years to reach the Earth, if they do reach the Earth at some point. Of course, most are just lost. Some fall into the sun, some escape the solar system. But we have collected on Earth over 300 meteorites that have come from Mars. We know that for sure. There's nothing ambiguous about that. We can measure the chemistry. It doesn't match anything on Earth. It doesn't match anything on the moon. It doesn't match anything on the other planets. It matches 1-to-1 the soil or the atmosphere of Mars. So we know that we are dealing with things that come from Mars. Now, they don't have life in them, except some ambiguous claims of things that might be forms of life, but that's very ambiguous and usually not considered to be sufficient evidence right now. But my point here,
would we, if we turn it around, just a quick question. If we turn it around, if an asteroid hit Earth and meteorites got spoon on Mars and landed on Mars, would we find traces of life in those pieces
exactly
of rock?
That's exactly it. The inverse must have happened. Earth has been hit by large comets and asteroids. The big ones would have kicked off Earth rocks into space. Some would have landed on Mars. We could have seeded Mars with Earth life, especially early in the Earth's history when impacts were very frequent. And so life could have evolved on Mars and turned into this thing with bones, but it would still be Earth life. It's not fundamentally a separate origin of life. So
it's not extraterrestrial life.
What we're looking for, that's the whole point. The whole point is to find the first example of something that is not of the Earth. Now, there are a few things that are interesting about all this. One is all life on Earth is genetically related. We all have different DNA, but all life on Earth uses DNA, and there's no exception to that. And and that's quite remarkable. And there were other options than the specific molecules that we use in DNA to make DNA. But the thinking is that that's actually one of the signatures of life. And in fact, all life forms on Earth share some fraction of their DNA in common, and which we believe goes back to a common ancestor that was in the form of a little microbe on early Earth. Now, the second thing that's quite remarkable, all life on Earth, is that all life on Earth has proteins. You have protein, you have proteins, we all have proteins. The proteins of life on Earth are made up of the same set of 20 to 22 amino acids. Most life forms use 20 amino acids. These are molecules that when you put them together, they make a protein. Some life forms use a set of 22 to make their proteins. But basically, among the thousands of possible amino acids in nature, life on Earth uses only 20 to 22.
21.
Okay.
Wow.
And not only that, but they only use the left-handed version of the amino acids, not the right-handed. So amino acids are complicated molecules, but they can come in two configurations. One that has a left-handed symmetry, the other one has a right-handed symmetry. It's the same chemical formula, but it's structured differently. One is the mirror image of the other. Life on Earth rejects right-handed amino acids, even if they are the same composition. It only accepts left-handed amino acids. Now, why? We think that that's just some quirk that dates back to early life on Earth. That's what we started with. We just kept doing the same thing. There was no reason to change. And that was it. So one way to identify that a life form is alien is to show that it doesn't use DNA, or it uses DNA structurally, but a different set of molecules for DNA. Or it has protein, but doesn't use the same set of left-handed 20 to 22 amino acids. Maybe it uses different amino acids. Maybe it uses the same amino acids, but the right-handed version. Anyway, any of those differences would tell you that the life form is not of the Earth. It's alien. Now, to do that kind of analysis, you have to find the life form alive. You cannot do DNA analysis or amino acid protein analysis on fossils, which is why I think this current search for life on Mars, roving around, looking at ancient rocks, looking at habitats where might be life. I mean, it's all very interesting, but it's not very strategic, because we're not going to find something that we can even test to be alien life. I mean, the fact that it would look weird doesn't tell you anything. I mean, all life on Earth, if you think about it, is pretty weird. So, weirdness in shape or form is not going to be a reliable indicator. Exactly. Now, here's some good news. We know that Earth rocks can travel into space and possibly reach Mars, because it goes back to Alan Shepard and Apollo 14. So Alan Shepard was the first American in space. He was a fighter jock, and he remains famous for being one of the astronauts who was the least interested in geology. Most astronauts went for Apollo astronaut training. They were learning about rocks. He apparently couldn't give a damn.
About those damn rocks.
It's just, he liked to fly planes, and he was just not into geology. So somehow he became commander of Apollo 14. And they were supposed to bring back, several hundred pounds of rocks, carefully selected, each rock about the size of a little tennis ball, to have a good, nice sampling of the diversity of the geology of their landing site. And instead, one of the first rocks he picked up was a giant, very heavy, basketball-sized rock, so that he could get to the mass limit very quickly, and did not have to pick up more rocks. And this rock that he picked up, that was very big, was famously called Big Bertha, which goes back to the giant tank or cannon that was used, I think, in World War I, called the Big Bertha. Anyway, Big Bertha is the name of that giant rock. And Big Bertha turned out to be not very interesting. I mean, it was a mixture of different rocks from different parts of the moon, but mostly locally and just welded together. And so the Apollo 14 was what, in 1971, Apollo 71, maybe 70. Yeah, 71. And Alan Shepard died, if I remember well, in 2011 or something like that. Instead of,
Mhm.
doing geology on the moon, he played golf. He famously played golf. People in the science backroom were furious
Mhm.
about the wasted science opportunity of sending Alan Shepard to the moon. But of course, he was a national hero.
Mm.
He was the first American in space. Um, but then in 2019, so just a few years ago, geologists have realized that inside Big Bertha, there's a little fragment of granite. And there's no granite on the moon. The granite would have only come from the Earth.
No.
So we now know that this little piece of granite is approximately 4.1 billion years old. And it is now the oldest piece of Earth rock that we have. No Earth rock goes beyond 3.944 billion years. This thing is 4.1. It is now the oldest piece of rock that's preserved, and it's inside a moon rock. And
So just I need to wrap my head around this. So Alan Shepard, through his ignorance, stumbles across a very rare meteorite, or a piece of rock from Earth on the moon.
The
Is that
Big
right?
Bertha is mostly moon rock. It's a tiny fragment that's embedded inside.
Yeah.
That is a piece of the Earth. Moon rocks are made of very heated fragments of other rocks because of impacts on the moon. It breaks everything up and then they fuse together. So this was a rock that was made of fused fragments of other rocks, mostly moon rocks. I mean, completely moon rocks, except for that one little fragment. That one little fragment is now the oldest piece of Earth rock that we have an example of, which makes Big Bertha super interesting.
But it could also be an indicator that the moon, as some argue, has been part of Earth in the first place.
Except that it doesn't work because that episode where the moon was created by a giant impact and incorporated pieces of the Earth, in that process, everything got destroyed. So that piece and that fragment actually is too young to go back to the beginning of that impact. So, 4.1, the Earth formed 4.5 billion years ago. So this is, we're talking about 4.1 here. So it's later. But nevertheless, it proves several things. It proves that Earth rocks can get thrown into space, at least small fragments, and land on the moon. But it also proves that it's pretty common, because what are the chances of Apollo 14 picking up a rock on the moon and it having a piece of Earth in it? So the community is quite excited about this finding. And it has implications.
Made only possible by Alan Shepard. Another
Alan Shepard,
astronaut
who never realized the value of his sample.
Fantastic. But you were mentioning that we're looking in the wrong places on Mars.
We now think that the surface itself is probably sterile. And it's going to, I mean, we have to establish a life is alien on Mars, if we find it, we have to find it alive. We don't think that the surface is capable of supporting anything that's alive. I mean, even extremophiles from Earth, life forms that are microscopic, that like extreme environments, can survive one or another aspect of the Martian extreme environment, the cold, for example, or the low pressure, or the dryness. But nothing on Earth can survive the full combination of these things at the surface of Mars today. And there's also the radiation. But as soon as you go underground, the situation changes completely. Many life forms on Earth could survive underneath the surface. So the only possible place, in my view, that we might find life on Mars that's still alive is if you go underground. Now, how far? Some people speculate that if you just go into ice in the ground, because the ice can go through cycles of freezing and thawing over long time scales, that might be sufficient for life to be preserved there in some sort of a hibernation form, microbes. But it's better to go deeper where you have enough temperature. It's a bit like in a mine where the deeper you go, the hotter it gets. So if you go deep enough on Mars, usually that means 2 to 5 kilometers. The temperatures become high enough where the water now in the ground is not frozen, but liquid. Now, that would be an amazing thing to do. Of course, it's very challenging. On Earth, we commonly drill to 3,000, 4,000 meters for oil. We're talking about 2 to 5,000 meters on Mars in very cold, frozen ground. It's a huge challenge for the future. But the other way to go underground is to go in caves. And the good news there is that there are several hundred caves that are now known on Mars. The vast majority of them are on volcanoes. And some of these volcanoes we think are probably still active. I mean, they're not erupting this minute. And we have never seen an eruption going on Mars. But they have been growing in size and they have been active for so long that would be very surprising if they were completely dead now. So some of the Martian meteorites are actually volcanic rocks that demonstrate that Mars was volcanically active just a few 100 million years ago. So I think that is the best chance for us to find life that's still alive on Mars, to go explore the volcanoes of Mars into some of their caves. And of course, you would go with robots first, eventually humans.
Are there any such missions on the horizon?
There's a lot of talk about it. There's a buzz, and we're talking about a new generation of vehicles. With the success of the Ingenuity helicopter, JPL is now designing a larger helicopter. I mean, if you have a nice big drone, you could fly into a cave, and sample it, come back. Yep. So I think the future is bright, but this very minute, we still have missions that are sort of doing things the old-fashioned way, and they're not going to get to the answer that we're really after.
So, Pascal, how about non-carbon based life possibilities?
Yeah. The reason why the speculation about that is because silicon, for example, is an atom that has the same valence, the same number of free electrons as the carbon atom. And technically, whatever molecule you can make with carbon, you can make with silicon. But the problem is the bond, like, for example, CO2, carbon dioxide, okay, it's carbon and 2 oxygen. You can make SiO2, silicon with 2 oxygen atoms. That's silica. Silicate. That's essentially quartz. Okay, well, you can make materials that use the same chemical bonding, but the strength of the bond is much stronger. It's a lot harder to break up quartz and sand than it is to break up a CO2 molecule. So the probability that life would use something that is so energy intensive for its biochemistry and its, it's just like saying that, well, not all life needs water. Maybe it can use, some other fluid. The fact is, water is a very common molecule in the universe. It uses 2 hydrogens and oxygen. There's plenty of both. And if you start speculating that, it could be using other compounds, you can't rule anything out at this stage of our ignorance. But the likelihood of life being based on anything other than carbon chemistry is very unlikely, actually.
So, in fact, if we wanted that kind of chemistry that you just mentioned, we would need to go to energy intense places like Venus,
Well,
for example, where you have like a lot more energy in
yeah,
the system.
but it's not just the heat, right? Because heat then comes with other problems with the availability of a fluid to hydrate a system, to facilitate chemical exchanges. So it's a bit of a catch-22. It's not. I don't think it's a lack of imagination in our heads. It's simply the limits of physics. You look at, there's a reason why something as complex as life, there's a reason why it uses the most simple chemical elements. It's because it gives it maximum flexibility. That's what really life needs. The more difficult you make chemical reactions, the more unlikely I think you make life.
Let's just jump to a different topic, Pascal. You mentioned before our call that you just got back from an Arctic expedition. So you're not new to it. If I remember right, it's you're way beyond 30 missions into the Arctic and Antarctic. Is that right?
So the Arctic is a place where we go every summer. I moved to California 27 years ago. I have yet to spend a summer in California. I don't know what it's like at the beach.
Fantastic.
I've heard about surfing, but it's a concept. Every summer of my life I have spent on Devon Island in the Arctic.
Wow,
and Devon Island is one of the most Mars-like places on Earth. It's the largest uninhabited island on Earth. It's in a corner of the Arctic that is not only cold but dry. All of Alaska, Siberia, all of that is pretty wet and grassy. Devon Island is rocky polar desert. In that sense, it's one step towards Mars. It's not as extreme as Mars, but it's one of those. It's the largest expanse of land on Earth that is both extremely cold and extremely dry at the same time. I mean, you have the mountaintops. Antarctica is like that, but Antarctica is mostly ice covered. Devon Island is mostly not ice covered. And on top of that, the island has a giant meteorite impact crater called Haughton crater. This thing is 20 kilometers across. So it's actually not too different from.
Let's just put that into perspective with the meteor crater in Arizona. That's
meteor crater
2 miles,
in Arizona
right?
is 1.2 kilometers. This thing is 20 kilometers, and and then it's even though it's 23 million years old, so it's not exactly young. It's still relatively young, and because it's been mostly preserved in this freezer of the Arctic, the whole thing looks like it happened just yesterday. If it was smoking, you would think it just happened. But it's an amazing place. And so we go there every summer in late July, August, to learn about the geology of Devon Island, because it presents so many things that look like Mars: canyons, valley networks, gullies, polygons in the ground ice, and different types of all of these things. So we call it Mars on Earth. But then we also use the place to test future technologies. So robotic rovers, Mars helicopters, spacesuits, and we're thinking ahead here at the future of human space travel. But a lot of things that we've worked on have ended up, helping shape missions that are now happening, both on Mars and on the moon as well. So anyway, this place is just an incredible place, and it's become my, second home. You're right. Aside from the COVID year where we went somewhere else, we've been going up to Devon Island since the year 1997.
Wow. So when you're talking about we, that
Mars
is the
Institute,
Mars
my
Institute.
teammates and I is mostly the we, and it's usually researchers, and a small core team of logistics teammates. And we have a permanent camp on Devon Island that's lined up like a Mars base. And if you want to see a little bit what we do, I would propose you go to YouTube and check out a link called Astronaut Smart Glove. So it shows you the landscape, our base, but also the type of work that we're doing to advance future human exploration. Astronauts.
Fantastic. So, in how far is that connected to the big agencies? Is there an exchange going on between NASA or other agencies?
We are funded by NASA. Yeah. We also have industry partners.
Okay.
On occasion, we've had ESA participation, Canadian Space Agency, of course, as well. Yeah, so it's an international project, actually, although it's mostly funded by the U.S.
So you're mentioning a 20-kilometer diameter crater. So what would that impact have done to Earth, to the biosphere? Would that have been a major impact?
It would have been, well, let's put it this way. It would have made the evening news. But it's not an evolution extinction event. It would have wiped out certainly life several hundred kilometers around Devon Island at the impact site.
And maybe cooled down the atmosphere
things
for
like that.
A little while.
It would have been a regional disaster, and it could have been a global. It could have had a global sort of fallout for a year or two, but ultimately it was not an extinction level event, Ely. But having said that, a few things are quite interesting happened there. First of all, a 20-kilometer diameter crater, you have to imagine, the shock wave expands through the ground at about 1 kilometer per second. And so a 20-kilometer impact crater takes about 10 seconds to open up. So imagine this asteroid or comet hitting, and it was approximately 1 kilometer in size and coming in at 20 kilometers per second. The impact, of course, the initial impact is a big, bright flash. Atmospheric shock wave, but then the crater cavity opens up, and you have to imagine this opening up in 10 seconds, a giant 20-kilometer hole in the landscape, with rocks getting thrown off to the sides. And then shortly after the crater formed, it was filled by water again. And the Arctic at the time wasn't as cold as it is today. It was, the Miocene, 23 million years ago. So, one or several lakes refilled the crater. And inside this lake, at the bottom of this lake, where there were lake beds that were laid down, sediments. And today, the lakes are gone, but the sediments are still preserved. And the beauty about these sediments is that they are now the only sediments that we have anywhere on Earth of what the Arctic was like 23 million years ago. There's nothing of the Miocene with that period. The Miocene is when mammals were getting really large. Mammals were all over the place. There was a little rhinoceros roaming the Arctic at the time. This was shortly after camels started to emerge in North America. And the lake beds are a treasure trove of fossils from what the Arctic was like 23 million years ago. And one major find, not by our project, but by Canadian paleontologists, is an interesting creature called Pugila darwini, after Darwin. Pugila darwini is considered to be the missing link between land mammals and the first seals and other pinnipeds, sea lions, seals, otters. All of these went back to sea from being land mammals, a bit like whales went back to sea from, being land creatures as well.
Mhm.
And the missing link for pinnipeds has been sought for a very long time. How did you go from something that looked like a beaver, we thought, to things that look like seals today? And that missing link, sure enough,
Mhm.
is a beaver-like thing with webbed feet, and that is found in the lake beds of Houghton Crater on Devon Island. And so
Wow.
I just love this place. It's an
Wow.
incredible place, both for the history of the Earth and for our future on Mars.
Is that like a sanctuary, a natural wildlife, or a natural sanctuary? Because I guess no one except experts should go to this place.
Yeah, you can go there. I mean, it's
Yeah.
Canada. You can go there. I mean, we need permits to access some parts,
Yeah.
including the lake beds. But it's a protected place, and of course we take good care of it. But we have a permanent base camp there, which we occupy only in the summer. And people who want to do research with us can basically contact us, and then we can make them part of our expedition each year.
Are you still looking for research coming into your field of experts? So are you still proactively looking for PhDs or whatnot?
Yes, always. The door's open. The way to contact us, we have the information on the Mars Institute website. You can go to marsinstitute.no. Our headquarters are in Norway, actually. marsinstitute.no/HMP, HMP, Haughton-Mars Project. And so if you go to marsinstitute.no/HMP, you can find my contact information and how to get involved.
Fantastic. Pascal, I'd like to.
Yeah, thank you.
I'd like to come to a very contemporary question we need to ask, because it seems like we're in a very decisive pocket in time when it comes to a technological leap we may be undertaking at the moment. If we take a look at what's going on in artificial intelligence, if we take a look at what's going on in space propulsion technology and space technology in general. So we got the Starship on the horizon. We got Blue Origin happening. We got artificial intelligence. We got pretty interesting things happening. So we've been talking now for quite a while about fantastic visions and projects that at some point could be possible and could help answer a bunch of the most profound questions we're asking ourselves. How far do you think are we from getting into a pocket in time where we are starting to answer those questions from a technological perspective?
Yeah. One of the biggest questions we've had looming before us since the beginning of science is the possibility of life on other worlds and the origin of life. I think the origin of life is going to remain a bit of a mystery for quite a while, but I think finding a first example of alien life is something that we might it might be something we encounter this century. And because we're starting to look, I think, in the right places, underground on Mars, eventually in the ocean of Europa, and also there's a mission called Europa Clipper that will explore, the possibility of life there. And then there are missions that are planned to Enceladus, which is a moon of Saturn that has an ocean underneath its icy crust as well, but where the water is jetting out through cracks.
It's that 300-kilometer deep ocean, right? That's mind-blowing.
So on Europa, the ocean is about 100 kilometers deep. On Enceladus, the ocean is about 60 kilometers deep. But it's still considerable, and I mean, to think about the fact that our own oceans, the deepest part is 11 kilometers. So 100-kilometer deep ocean is Very
is
scary.
damn scary. It's underneath an ice sheet, right? And so anything could be happening.
It's underneath an ice sheet that's, it's about, 10, 20 kilometers in thickness.
Both results are scary. This place being empty is scary already. Completely void of anything is very scary. At the same time, it's very scary if it had life or teeming with life. That's equally scary.
Yes. Yeah, I agree. But it's so exploration worthy. So I do think that we're going to find a first example of alien life this century. It will take some time, but and my guess is that we'll find it on Mars before elsewhere. As far as other big questions, I would be very surprised if we found an alien signal from an alien civilization anytime soon. I mean, it's my view is not the most popular one at the SETI Institute, but my sense is that we might be in our own galaxy. And then bear in mind that even if a civilization can communicate, it doesn't necessarily do it. So,
but they may inadvertently communicate, like our electromagnetic, our television radio waves we've been transferring into space. So I think at our outmost layer is about, 100 years, 110 years, light years.
Yeah. So, yes, and of course we're not necessarily emitting very powerfully with any of these systems. There's also, mention of the fact that at some point we can move away from radio waves and go into, lasers and optical lasers and cable. So there might be a window of time when civilizations are loud in radio and then they become quiet again because they use other technologies. So anyway, the thing is, I don't think our chances are good of detecting anything alien out there. Now here's a wild card. I don't believe that any of our UFO sightings are a manifestation of an alien spacecraft. Okay, I mean, I think there are some mysteries that we have to resolve. But Carl Sagan used to famously say, "Extraordinary claims require extraordinary evidence." All right, so if you make the extraordinary claim that something is an alien UFO, you have to present much better than a fuzzy picture.
Yeah.
Or
it's
fuzzy
always
video.
Those fuzzy pictures. We're in an 8K era of technology and still we're producing only fuzzy pictures.
Yes. And, Jill Tarter, who's one of the scientists at the SETI Institute, she's retired now, but she's the character upon which Eleanor Arroway in Contact is based, the Jodie Foster. She gives a talk where she explains that, for a while, they had this video of a black dot on a windshield. You could see the black dot in the sky, and it was doing these zigzag motions, and then eventually it just took off. And it turns out that it was a fly on the windshield. Okay. So I'm not saying that they're all like this. What I'm saying is there are lots of things that you have to be really careful before you jump to the ultimate conclusion. But, if we're really open to the idea that civilizations can reach such a level of advancement that, they can travel through wormholes and time tunnels, space-time tunnels, if that is possible, well, then it's not a crazy idea that they might have come by. I don't think, on the other hand, that we'd be very interesting for them. I mean, maybe if there was an sort of a primitive biologist among them, we might be interesting, but maybe
But
not.
isn't it also very interesting that those visitors keep coming in flying objects, but then disappear again. So if I were an alien civilization, I would perhaps try to land on that place.
Yeah, and of course, every now and then you have stories of crashes,
Yeah.
and the thing is,
Yeah.
shouldn't they have fixed that problem by now? But joke aside, there's part of me that wants to be open to the idea that, hey, technology could be so far advanced that we might not even be able to detect it or comprehend it. Arthur C. Clarke famously said that any technology that's sufficiently advanced is indistinguishable from magic. And so as a scientist, you're reluctant to believe in magic. But meanwhile, that's what you would expect if you were actually faced with a civilization that is very advanced. But my point, though, is that I don't think we're dealing with a lot of civilizations, and extragalactic travel is something really wild. It might be possible through wormholes and space-time tunnels, but in our galaxy alone, I'm guessing that we're close to being alone, and so we should. I think we're facing a very bright future of exploring our galaxy and searching for life and trying to understand better how life forms. But we're unlikely to find anything that we can really talk to.
How's that make you feel personally?
Still very excited. I mean, it's an intriguing universe.
I like that. It's an intriguing universe. I like that one.
You never know. You could still run into something that's intelligent.
But it just, but yeah, I don't know, Pascal. It drives me crazy, the sheer thought of the vastness of all this and the emptiness, and most probably not having a prime mover behind all this. This drives me literally crazy whenever I think about it. There's the sheer existence, the weight of sheer existence, a mediated existence. This is majorly fantastic.
Yeah, you bring up a profound point, I think, Marcus. Even though we might be alone in our galaxy, it still doesn't make us the product of divine intervention. We're still a circumstantial product of random evolution, and
the playground is just big enough that to make something happen. Like the playground is so huge that life came into being.
Yes, exactly. We are both unintended,
yes,
but at the same time, so special. So
I like that.
We should appreciate
Fantastic. Pascal, if the call came right now, if you wanted to board a spaceship leaving tomorrow, traveling to Mars, or say next summer, would you trade it for the Arctic?
Oh, yeah, of course. I mean, I've lived to go to Mars one day all my life. I mean, the every year that goes by makes it less likely. But, it's both a big trip and not a big trip. It's the next planet over, so I tend to not make it a big deal, although I also think that most people don't quite realize the challenge that it presents to us, the way technology is today.
But still,
I think it's something.
No.
Yeah.
Still, it's quite a journey, taking up quite a bit of time. So my question to you, and I keep asking that question to each of my guests on this show, it's going to get very boring at some point. After 3 weeks and after the first excitement has worn off on that spaceship, things are getting boring, I guess. So my question to you, what would be the one piece of music you would want to bring with you? And it's just one tune you can put on that playlist. You wouldn't want to miss to cheer you up through dark times.
one piece of music. Also sprach Zarathustra.
All right.
Johann Strauss.
Yes, fantastic. In fact, we do really have a playlist for the aspiring space traveler on Spotify, and it's populated by all my guests and their selections. So thank you for your contribution to that one. And now go ahead.
Yeah, you mentioned boredom.
Yeah.
You know, I many years ago, I had a chance to. I mean, I grew up in France, so at the time there was still a national service, and when I finished school, I still had to do a year in the national service for France, and so 3 years ahead of time, I applied for the one position that they offer each year for a geologist to go to Antarctica. And I was lucky enough to get the position. So I went to Antarctica and I spent a year there when I was a young man. And that, of course, whole experience changed my life as that I was expecting it to. But it was like living on a different planet for an entire year. It was just an amazing experience. I mean, as a kid, I'd grown up in big cities. I was born in Hong Kong, so skyscrapers. I then went to school in Paris. And so Antarctica was a different planet for me.
Wow.
But we were allowed to take 2 trunks of personal effects. And I was so concerned that I might get bored that I took, an entire trunk of books. And at the time, there was no internet.
Yeah.
Or I'm going to date myself, but there was no internet. There was nothing. So I took a whole trunk of books, and I ended up not being able to read more than about a quarter
in a year
of the books I took, because it was so exciting to just be there.
Wow.
The work, even though it was routine, was interesting. The whole experience was worth writing about. So my point here is that, you don't want to be sending people who tend to be bored.
Exactly.
Okay, to places like, they just shouldn't go.
Yeah.
I mean, until it becomes, until you have in-flight entertainment all the way, you should be going to Mars. But if you are really motivated to go to Mars, you are really absorbed by the journey. The boredom is not even a factor.
Yeah, completely right. Pascal, this place is called the Space Cafe Podcast. It's a coffee place, so to say, where we hang out to chat with one another, to nerd out. In coffee places, you now and then get yourself an espresso to energize yourselves. So why don't you share, and I would like to challenge you now to share an espresso for the mind with me and your audiences. Pick whatever kind of thought you want to pick, but it should be invigorating, inspiring, and energizing for the audiences. So pick whatever you want to pick.
I think we're going to be building a base on the moon very soon. I think that's what we should do, because that's the only way to actually explore things with any long-term capability of growth and strategy. And lately, I've been working on trying to find some good places on the moon where you could build a base. Even though we're attracted to the polar region, especially the South Pole of the moon, those are actually not good places to set up a base. I mean, once we find water and we determine that we can actually extract water economically, water ice, we can then do a mining operation there. But until then, you don't want to set up a base there. Meanwhile, we need a base as soon as we can. So I've been looking around, and one of the best places actually we found so far is Clavius. Clavius. It's a crater on the near side. If you look at the moon, it's near the 7 p.m. location. Clavius is the second largest crater on the near side of the moon. It's one of the oldest craters on the moon. And it's where 2001: A Space Odyssey actually had its base.
Wow.
So I'm excited about this idea that we might actually turn 2001: A Space Odyssey into some sort of a reality.
And find that monolith on that site.
I don't know about the monolith, but as much as I'm more of a Star Trek and the Star Wars generation kid. Those are completely fantasy worlds. 2001: A Space Odyssey is, forget about the schedule, but it's showing you, I think, some correct steps. So a base on the moon at Clavius is something that could become a reality here in the next, decade or two.
Wow.
And then beyond that, there will be the journeys to Mars. We will explore the moons of Mars, Phobos and Deimos. But beyond that, I think we should go to Titan, which is one of the largest moons in the solar system, the largest moon of Saturn, where there's an atmosphere on Titan. Titan has such a thick atmosphere; it's thicker than the Earth's. The Earth's atmospheric pressure is 1 atmosphere. Titan's atmospheric pressure is 1.4, so it's 40% thicker than even the Earth's atmosphere. Meanwhile, gravity is less than even on the moon, on our moon. So it's very easy to fly on Titan. And so with a student earlier this year, we designed first of all, a spacesuit for Titan. And you should realize that a spacesuit for Titan, because the atmospheric pressure is so high, it doesn't need to be a pressurized suit. It just has to keep you very warm.
Wow.
The temperature on Titan is, minus, I have the number in Fahrenheit in my head, so minus 200 degrees Fahrenheit. So it's pretty cold. It's, minus 190 Celsius, something like that, to be checked. But the point is, as long as you stay warm, and of course you wear a face mask to give you breathable oxygen, the spacesuit can be quite simple. And so, as far as it's going to be to get to Titan, I mean, it might take 5 or 6 years to get there for a human crew. Once you're there, you actually are in an environment where it'd be less hostile than the moon.
Wow.
Or even Mars for that matter. Both Mars and the moon, you spring a leak in your spacesuit, you're dead.
Yeah.
On Titan, you're not necessarily dead if you spring a leak in your spacesuit.
Wow. So what's the atmosphere made up of?
Mostly nitrogen, which is amazing.
So if you bring your own oxygen, because in fact we breathe nitrogen also, of course. So if you bring your own oxygen, you should be good.
Yeah, and in fact, the spacesuit, I'm having people breathe nitrox, which is a mixture of oxygen and nitrogen.
Scuba diving.
So that it's very similar to the Earth. I mean, you would have more oxygen, less nitrogen to breathe, but you just have to keep very warm. And of course, there's some toxic gases in the atmosphere, like hydrogen cyanide. So you don't want to take a deep breath of the Titan atmosphere. But those can be repelled. And handled quite easily with a chemical suit type of thing.
Yeah.
Anyway, we have the message here is that there are exciting times ahead, I think, in space, and a base at Clavius and humans on Titan. Something for early next century, maybe.
Fantastic. Pascal Lee, thank you so much for taking the time. This was, mind-blowingly interesting.
Thank you, Marcus. Same here. I really enjoyed this. I'm glad we went into some depth here.
And that's a wrap, my friends. With Dr. Pascal Lee, I mentioned in the very beginning that I couldn't wait to let this episode off the hook, and perhaps you will understand now how I felt when recording that one. It's truly mind-blowing. Thank you, Dr. Pascali, for taking the time and sharing your wisdom again. So quick recap. Challenges of finding intelligent life out there. So it's still quite tricky. So maybe we need to extend our horizon, and maybe we need to employ artificial life, artificial humans, in order to venture out into the vast unknown, because the distances are mind-blowingly large and vast. So the biological life may be the wrong life to engage in such endeavors. If we want to get a little bit closer and maybe use biological humans in the search for extraterrestrial life, maybe we should go back to Mars again and look a little deeper. Maybe we have been looking at the wrong places ever since we started digging around Mars. So perhaps a couple of meters deeper and we would stumble across, I don't know, ET or whoever ET is up there. And of course, I loved that Big Bertha story. Alan Shepard, thank you for your disinterest in geology. What a fascinating story. Just picking up a rock I mean, like, what are the odds you pick up a random rock on Mars? I mean, like, Mars, not on Mars, on the moon. That's not like around the corner. And then you stumble across a piece of Earth. Not the moon, but a piece of Earth. That's a lot older than anything we've come across on Earth. I mean, like, what are the odds again? So, my friends, if you like what we're doing here, why don't you give us a bunch of ratings or reviews wherever you're listening to those podcasts? And I love multiplying by word of mouth. So maybe tomorrow or today you happen to come across a person you feel like could dig what we're doing here. Invite them into our circle of trust and tell them that we exist. This would mean the world to me and us, the team of the Space Cafe podcast. So that leaves me now with I can't tease the next episode because I haven't recorded it. So I don't even know what we're going to be doing in 2 weeks from now, because a bunch of scheduling has gotten mixed up. So we'll find out. So I'm going to be surprised. And so I will surprise you with something. And what else? Well, that's about it for today. Stay curious, my friends. And thanks for your growing interest in that show. And I'm signing off for today. And I'll find out what we're going to be recording for next time. Take care, my friends. Bye-bye.